Exactly.
Alright.
You don't stop master.
I found out that we cannot do the test yet. We have to do something more. Okay, the assignment.
Yes.
Let's do correction to it.
No, not do the correction. Let's do it.
Now only pen.
Now, person will tell me for correction.
Now only pen and things.
Can't do that.
Let's solve number one. Let's solve number one. Let's solve number two.
Yeah.
I don't know how to go that far.
I'm not starting.
Let G, H, and A be differentiable vector functions over a region D, and phi be a differentiable scalar function over the region D, so that G equal to blah 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 satisfy the equations this and that. You don't complete the question.
You're not completing that.
No, the other one is there now.
Okay.
I've also got that.
So you solve one.
Alright, so that means that, listen. So if you read the statement carefully, you will notice something here that you're given let's say 5 equations, and you want to use those 5 relationships to actually prove statements 1, 2, 3, 4. Okay, you have been told that, please pay attention, show that G equal to this and H equal to that satisfy these 4 equations, provided the following conditions are satisfied. So provided that this is the relationship between them, alright, where C is a constant and rho is a scalar function. So we have 5 relationships. So we have been told that G, okay, is equal to minus lambda 5 minus 1 over C del A del T. And we have been told that H is equal to lambda cross A, okay, and then we are also given that these conditions are satisfied. These conditions are also part of those things we are given. So we want to say that is to have lambda dot A to be plus 1 over C. That's the first condition. So I can say this is equation, let's say equation A. Okay. This one is equation B. Lambda dot A plus 1 over C del phi del C equal to 0. So I can call this equation C. This is one of the conditions that are already satisfied. Don't get it twisted. These are definitions of G and H. These are equations satisfied by, G, H, and A. And these are equations satisfied by G, H, and A. Do you understand what I'm saying at all? Alright, so we will use both the definitions and also the conditions they satisfy to show that the equations given to us are true. Okay? So we say that the second one is that lambda square 5 is equal to 1 over C squared, then square 5, then C squared. And then the last one, lambda square A, so lambda square of a vector, is equal to 1 over C squared, then square A, del C squared. And then we are told that. So we have all these conditions, all these statements already given to us. So we will use all of this to establish the first statement. So the first one is we want to show that, number 1, we want to show that lambda dot A lambda plus H. We want to show that lambda plus H equals 1 over C del T. What is it? Minus
5.
No, that's one of the things we want to show.
Yes.
Is there another one that has no point?
No.
The question.
That question will be equals to last one. It's one of the things we want to show.
Okay, it's the question, not the condition.
One of the things we want to show.
Yeah, I can't try.
Okay, so this is the first one. So it means that we want to show that this thing nabla cross h is equal to this, where nabla, so where h is defined this way, and these conditions also hold for h, a, and others that we have been given. So let's see. So we go from the right hand side and see how it gives us the left. So we go from the left hand side and see how it gives us the right hand side. So nabla cross h. What do you think this is going to be? Nabla cross h. You have been told that h is nabla cross a. So I will substitute that. I know nabla cross h will be equal to nabla cross a. Does that make sense to you? This will follow from equation a. You understand that? Is that clear? From a, this will be equal to, okay, b, sorry, b. So we have this expression, and please pay attention. So when you have vector triple product, can you remember vector triple product like this? One of the properties of vector triple product that we considered the other day was that you have something like a cross b cross c, something like this. It can be written as a dot c is b, abi, minus a dot c, a dot b c, a dot b. Alright, so similarly, I can use that to simplify this expression. So I'm going to have something like this. So I'm going to ask that nabla dot a, abi, multiplying nabla, okay? But if I put nabla, you know that I could put nabla this way, but it doesn't matter actually in this vector relation here, I put this v here. Do you understand what I'm saying at all? Because this one is scalar multiplying the vector. Is it making sense to you? So I can write this as nabla dot a, okay, multiplying the nabla. That's nabla of nabla dot a, then minus, I will then do this. That will be nabla dot nabla, abi? Nabla dot nabla is nabla square. Is it clear? That will be nabla square e. That will be minus nabla square e. Does it make sense to you? Alright, so I can simplify this, that. And with this, I will come here again. You can see nabla dot a is equal to this. I can move this to the other side. Nabla dot a will be equal to minus 1 over c del phi del t. Does it make sense to you? And then I can also substitute for nabla square a is equal to 1 over c square del square a del t square. Does it make sense to you? Yeah. Alright. So when I do that, I'm going to say this is equal to nabla of nabla dot a, which is going to be minus 1 over c del phi del t. Does it make sense? Yeah. Right. Then I'm going to add this to the minus nabla square phi. That's going to be 1 over c square del square a. Nabla square a, right? Del square a del t. That simplifies the work. Does it make sense? Yeah. So I know this is a constant. This is a differential operator. This is a constant. I can move out the constant. Do you understand that? So I can say that this is minus 1 over c nabla of del phi del t, okay, minus 1 over c square del square a, okay, del t square. Again, I know that this is a differential operator. This is also a derivative, and the phi is differentiable. So for a differentiable function, the order of partial derivative does not matter. It's a partial differential operator, so I can divide the two nabla of phi first before differentiating with respect to t. Does it make sense to you? So I can move out the t. Don't get this. This is from equations which are done. From equations c and e. From equations c and e. So C and E. Alright. So I can move this out. I'm going to add it to be minus 1 over C del T of nabla phi. Does it make sense to you? Do you understand that? Alright, so I can write this way. So this will be equal to minus 1 over C square del square A del C square. So have to do this with our destination in mind. What is our destination? We want to arrive at something like this. Minus alpha g, now this is our minus lambda phi, then a del t. You can see that we are already approaching lambda phi, then a del t. If you can break this down, so that we will have then a del t outside. Do you understand what I'm doing at all? Do you understand what I'm doing? Okay, I want to have 1 over c del g del t. I know g is defined this way. I already have lambda phi in my expression. I already also have del a del t in my expression. Does it make sense to you at all? So to arrive at my destination, I can move out 1 over c. Is it clear? So when I move out 1 over c, I'm going to have this will be 1 over c. I can also move out del t, del t. Abi, this is del t. This is also del t. Is it clear? So I can have 1 over c del this del t. So what will I have left at the end of the day? This will be minus abi lambda phi minus. I moved out 1 over c. This will have 1 over c left. Is it clear? Because I moved out 1 over c. This is 1 over c. I move out del t. This will have another del t left. So there's a del t. Does that make sense? You understand that? This is the same thing as g from the first thing. Does it make sense? What I have in that bracket is the same thing as g. So I can put that here. So this is going to be equal to 1 over c del g del t. Again, from does it make sense? So that satisfies that point. Right? To satisfy that equation.
Okay.
Okay. I believe we can do this now. So you look for the definition of G. This is G. So you do lambda cross G. Lambda cross this. And then find out what you do. That's the next. Can you give it a try? So lambda cross G will be equal to lambda cross. What is G? G is defined this way. So I'm going to put this in for G minus lambda phi minus 1 over c then a del t. Does that make sense? That's from equation A. And then this will give us what? It will be equal to. Can you remember? Of course, this is going to give you, when you open the brackets, I can move out the negative sign. It's going to give us something like minus lambda cross lambda phi. No, the cross product operation is distributive over addition. So this is going to be minus. Again, I have 1 over c, so I can put out 1 over c lambda cross then a del t. Does that make sense? Do you understand that? Okay, so don't forget this is rotor of gradients. Abi? I know that rotor of gradients is 0. There's no need to work it. Abi? From the rotor, you know that rotor of gradients is 0. Is it clear? So definitely this one is going to be is that clear? Rotor of gradient is 0. Can you remember that? Rotor of gradient is 0. That is going to give you 0. So I have to minus 1 over c. Minus 1 over c. So what's our destination? This is where we want to get to. 1 over c del h del t. So I can move out this del t. It's going to be minus 1 over c del t of lambda cross t.
Now, so the entire.
You get that? Do you understand this? Do you understand this? Alright. So we are approaching H. H is lambda cross A. Can you see that? H is lambda cross A. statement to be minus 1 over C. Then H that is the result. Let's carry by your own.
No, they doubt me. No, they doubt me next time.
Swallows log.
Waiting for example, run towards my side.
Just move on to the answer. Okay. Exactly. I see that they are very simple. They are very simple. Almost as though the seemingly complex questions are usually the simplest ones. Some are very complex. Like, how we will really right. Okay, look at the next one. What's it? Next thing. Nabla dot H equals to
Gradient of group.
Nabla dot Nabla dot H. Because Nabla dot what is H? H is divergence of rotor is 0. You understand that? Divergence of rotor is 0. Just write it down that divergence of rotor is 0.
I'll let you understand.
Yes, now.
Okay, let me understand the rule.
They are not proving that the divergence of rotor is 0 now. They are showing that the statement is divergence of rotor. What's the last one? Nabla dot G. Four by root. Okay. What's Nabla dot G? This is Nabla dot G equal to Nabla dot. What is G? This minus Nabla 5 minus 1 over C then A del T. So everyone should be done with this by now. Nabla dot minus Nabla dot Nabla 5 minus 1 over C Nabla dot then A dot C. That next is going to be equal to Nabla dot Nabla 5. That's Nabla square 5. You get that? Nabla dot Nabla 5 is the same thing as Nabla square 5. So that's going to give us this. So I'm going to have this to equal minus Nabla square 5 minus 1 over C del T of Nabla dot T. Is it clear? So what is Nabla dot T? You have Nabla dot T to be equal to this. So you can put them together. And then you have Nabla square 5 to be equal to this. Oh, one of them should carry 4 by load. One of them should carry
I tried it.
okay, so the second one should be Nabla square 5. Plus 4 by Are you okay now? Yeah, yesterday there is an examination by Good. Minus 4 by Look at something else. So we're going to have this. And so lambda square 5, I'm going to put in that expression for lambda square 5. This is going to give us 1 over minus lambda square 5. 1 over c square del square 5 del c square minus 4 by 2.
What's happening now? That's the start. What's happening?
Lambda dot A is going to be minus 1 over c del 5 del t. You get that? So this is going to give us this. This is going to give us 2. We're going to have this to be minus 1 over c squared del square 5 del c squared then plus 4 by rho. When you open this bracket, notice a constant can be brought out of this is going to be equal to plus 1 over c squared. This will be del c of del 5 del c. Does that make sense? So this is going to give us minus 1 over c squared del square 5 plus 4 by plus 1 over c squared del square 5 del c squared. This makes sense. You understand this? Alright, so this is the same thing as this. You cancel out. Is that clear? So at the end of the day, you're going to have this to be equal to 4 by 4 by rho. Not that about that. 4 by rho. You get it? Behavior of the gradient field. Behavior of the gradient field. Behavior of the gradient field. What is the gradient field?
Vector that results from the gradient of the scalar.
Yeah, vector field that is the gradient of a scalar function. So gradient field is actually a vector field given by lambda 5, where phi is a scalar function. So once we look at the different behaviors of this, say different applications of it, implications of the gradient field. Okay? So please pay attention now. That means we are looking at some vector field or some vector function, which is the lambda of some scalar function phi. You see, making sense? Okay? So we use this to define directional derivative. So we say that it defines directional derivative. Okay? So what do we mean by directional derivative? From our works last semester on partial derivatives, you remember that we talked about if you have a function, let's say you have some function f, or in this case let's use phi. You have some function phi, of course, which depends on x, y, and z. We know that the total differential of phi, which is the phi, can you remember the total differential? The total differential of this will be given by, can you remember this? Del phi, del x, dx, plus del phi, del y, dy, plus del phi, del z, dz. So, this is the total differential. But if I desire the derivative, that's the total derivative of phi, okay, along some direction, I will have to do something like this. For instance, if I desire the derivative of phi with respect to some parameter t, this will be given by del phi del x multiplied by x. You understand that? I will divide by multiplied by the x. Just like I'm dividing it by this. Is it clear? As if I'm dividing it by this. Then plus del phi del y multiplied by dy dt plus del phi del z multiplied by dz dt. Does it make sense to you? Alright, so this is going to be the derivative, total derivative of the function phi with respect to some parameter t. But actually, what do we have here? You know, I can regard what I have here, this expression, for instance. I can also write it as, if you notice, I can write this as nabla. Okay, we write out nabla, let's just say nabla phi. Okay, so nabla phi is del phi, you know, it will have component del phi del x, del phi del y, del phi del z. When I take its dot product with the r, okay, where r is our position vector, you can remember our position vector, r equal to xi plus yg plus z. That's the position vector. So I want to take the differential of this. That will be the r equal to, that will be del x, the x, del x, that's 1, multiplied by the x. So the r is just going to be the xi plus the yg plus the z. Is that very clear? So if I take nabla phi multiplied by the r, those product of it, I'm going to have something like this. Nabla phi not the r is going to be equal to what? I del phi del x plus j del phi del y plus k del phi del z. It does the r, that is going to be what? The x I plus the y j plus the z k. Does it make sense to you? When I take the dot product, this will go with this, That's exactly what I have here. The phi del x is the x, the phi del y is the y, del phi del z is the z. Does it make sense to you at all? Alright, so that means that if I want to get this total differential, for instance, I could have done something like this. Is it making sense to you?
Yeah.
Okay? I will get it. And similarly, that means that what I have here, you know, is the same thing as the r dt. From this expression, you know, the r dt is going to be equal to, the r dt will be equal to the x dt I plus the y dt j plus the z dt k. So basically, what I have on this side is the same thing as having nabla phi multiplied by what? The r dt. That means that I can use this to obtain the directional derivative. Okay? This will give me listen now, what do you mean by directional derivative? It simply means the derivative of the function phi, okay, in a direction defined by the parameter t. Okay? That means if I want to define the direction, I will write x, y, and z. Okay, I will write r in terms of x, y, and z when it is already parameterized, according to this. We will take an example, you get what I'm talking about. This is going to give you the directional derivative. So that means that in this case, this is what defines the direction. That means it means that I want to take the derivative of phi in the direction given by r. Does that make sense to you at all? You understand what I'm doing? So I'm going to do this, and it's going to give me this derivative. And you see how to evaluate this. So let's take an example and see how this works. So typically to get the directional derivative, this differential denominator will not just be that of any parameter. We will use that of s. We will use the differential ds. And the s is the modulus of this. That means if you are going in a certain direction, listen now, if you are going in a certain direction, we say that this is going to be modulus of the r. This is going to be the magnitude of the r. Just act less. It means that, for instance, if you are going in the, let's say we have the x, y plane, and then let's say you are going in a certain direction defined by this. Arc length simply means that you just want to pick some length, give some differential length along that direction. And the length of it is going to be, this is what we mean by the R. So let's say we decided position vector L. This is the position at some distance, and then this is the position at another distance. Let's call the R prime. Okay? To change the R, that's what we mean by the R. Okay? That's the differential change in R. You can see this small length here. That small length is the R. Okay? Its modulus is what we call the S. So we have this thing to be very, very small. Please pay attention. If you have this arc length to be very, very small, that is, if I'm picking two positions that are very close to each other, then the arc length is going to be, the arc length is going to be approximately equal to the modulus of the change in R. Okay, so we usually use the change in R as the denominator. So if I do this, use this change in R instead, I'm going to have like the R, the S. Of course, it will be of the same form. That's going to be equal to the X, the S, I, plus the Y, the S, K, plus the Z, the S, K. Okay? That is, yeah. So the T is just any parameter. So we're not using any parameter to get the directional derivative. We use a specific parameter where S is defined as the arc length along the direction of interest. Okay? So the S is the modulus of the R. Okay? So the R is the differential of the position vector. So if we do that, that means in this case we're going to have define the S. So I want to get define the S, define the S, just like we have define the T on that side. This is going to be equal to nabla phi dot the R over S. Okay. So this is getting confusing now. Alright, listen. What we used earlier, the T. Okay, just imagine that you are changing all the T's to S. You understand what I'm saying at all? Why are we changing it? We want to give it an interpretation that this is not just any parameter that you can use. It is a parameter defined by the arc length along the direction of interest. What we mean by this is that we want to get the derivative of phi. That is, we want to get the derivative of this function along a certain direction. Okay? For instance, if you have a function, let's say you are dealing with the xy plane. This is x, this is y, and you have a certain function. Let's say you have this function. Let's say y is equal to whatever. Let's say y is equal to f of x. If I want to get the derivative, okay, with respect to x, I will say I want to obtain the y, the x. That is quite straightforward to do in 2 dimensions. But if I'm dealing with 3 dimensions, I will be dealing with the surface. And so I cannot just say I want to get the derivative of that particular function. For instance, in this case, you have y, y to just be a function of x. Now, what if you have a function phi, which is actually dependent on x, y, and z, and I want to get its derivative in a certain direction, an arbitrary direction given by the position vector r. Do you understand what I'm saying at all? In the case of the y dx, it means you want to get the derivative or the change along the direction of x. Is it making sense to you? You get what I just said? Okay. So, but in the case where I want to get the derivative of a function that is defined by these 3 variables along a direction defined by the vector r, then I am going to have to use my denominator here. Okay, instead of having just any parameter dt, this has to be the s, which is the differential length, differential arc length along this direction. That's what we mean by that. Just like here, if I want to get the derivative of y with respect to x, I will use the x. What is the x? The x is the differential length along the x direction. Is it making sense to you at all? So, if I want to get the derivative of this along the direction given by r, then I have to use the denominator as well. Differential length along the direction given by r. You see very clear now? Do you understand this idea? So that's what I mean by this should not be just any parameter. So it has to be the s, where the s is the differential length along the direction given by r. Is it very clear now? So that means that if I want to go in the direction of a, for instance, let's say I want to get the derivative of this vector function, this scalar function, along a direction given by some vector a. That means in this case now the direction is defined by vector a. What am I going to do? That means I'll be interested in the differential length along this direction of vector A. Is it very clear? Do you understand this idea? So what am I going to do at the end of the day? One thing you should notice here is the fact that what you have here is the same thing as the unit vector in the direction of R. Is it clear? Because you have the differential vector over its modulus. Is it very clear now? That means generally, if I want to get the derivative of this in the direction of the vector A, I can just go and get this as nabla 5. Okay. That will be equal to nabla 5 plus A all over modulus of A. Or I can write it as just nabla 5 multiplied by A cap. Does that make sense? Is it clear? That is the same thing as it's going to give us our results. That means I'm getting this in the direction of A. So this is the same thing as having the 5 in A. Is it clear? Alright. With respect to that direction defined by A. So that's what we mean by that. That's what you have at the denominator. Although it could be anything, but it should not be just anything. If you are interested in the directional derivative, it has to be the differential length along the direction given by A. Vector. Along the direction of
That's okay.
You know the easy as is. You just need to come.
Find the directional derivative of 5 equals x squared minus 2x squared y plus yz. Find the directional derivative of 5 equals xz squared minus 2x squared y plus yz cubed at the points 1, 3 minus 2. At the point 1, 3 minus 2. In the direction of A equals minus I plus 5j minus 3k. Did you get that? Find the directional derivative of 5 equals that. We have 5 on the board. This is 0. That's what's on the xc squared minus 2x squared y plus yz cubed at the point 1, 3 minus 2 in the direction of A equals minus I plus 5a minus 3k. You get it? Okay, look at the board now, look at the board. So, listen. So the usefulness of nabla, like we just saw now, is that, listen very well, please, listen. For me, I feel that when I needed to get the derivative of nabla, of 5, in the direction of r, I could easily do that by carrying out this, by carrying this out. And I could see that what I have here is, the differential in the direction of r, and I'm dividing by its modulus, which means what I have here is just the unit vector in its direction. Is that very clear? Yeah. So that means that if I desire the derivative of nabla of 5 in any direction, what I need to just get is obtain nabla 5, then dot it with the unit vector in that direction. Is that very clear? Okay, so I know that I have nabla and I have 5, this function. I want to get its derivative in this direction. Just like I told you, the y, the x simply means I'm interested in the derivative of y along x. Is it very clear? So in this case, I'm interested in the derivative of 5, which is a function that depends on x, y, and z. It is not just a function that depends on only x in this case. It's a function that depends on x, y, and z. I may be interested in the derivative in different directions. So what I will now do is to use this idea of nabla. Right? So this will help me out. So I want to get this derivative in the direction defined by this vector. Okay, so what do we do here? That means if I want to get this derivative, the 5, the whatever you have used for this parameter, let's say x, is going to be equal to nabla 5, dot the unit vector in this direction. So I can call the unit vector in this direction A cap. Is that very clear? So to give me the directional derivative of this. So what is our nabla phi? Nabla phi is going to be equal to I del phi del x plus j del phi del y plus k del phi del z. Okay, thus unit vector in this direction. The unit vector in this direction is going to be minus I plus 5j minus 3 divided by the modulus of this vector. So that's going to be square root of minus 1 squared plus 5 squared plus minus 3 squared. Does that make sense? Right. So we can carry out this. This is going to give us I del phi del x. So I'll come here and find out what del phi del x is. Del phi del x is what? So that will be z squared, Abi, minus 2xy. I mean minus 4xy. This is going to be z squared minus 4xy. Does that make sense? Do you understand that? So we can do that. We can do them separately. So we just put them together one by one. And the phi is going to be equal to I z squared. So when I differentiate with respect to x against this square, when I differentiate with respect to x, that will be minus 4xy. So that's minus 4xy. Because I will not carry x, that is out of it, plus j into, so I differentiate with respect to y. This is 0. For this, minus 2x squared. That will be minus 2x squared. And for this, plus z cubed. Then plus k into derivative with respect to z. That will be 2zx. 2x z. Then this is what? Plus 3g squared y. Abi?
Yes.
So that is our nabla phi. So we want to get, listen now, we want to get it at a particular point, and we want to get it at the point 1, 3, and minus 2. You know, this should not sound strange to you. Just like you can get derivative of a function. Let's say if you have a function y equal to f of x, you can get the derivative at the point x equal to 2, for instance. Do you understand what I'm saying now? Which we usually call f prime of 2. How do you get that? You can differentiate the function. When you have differentiated the function, then substitute 2 into it. Is it very clear? Is it clear? Aha. So it's the same approach here. I just want to substitute the values of x, y, and z into this. So that means we are evaluating this at this particular point. Does that make sense to you? Okay, so we can do just that and evaluate this at that point. So what is that going to give us? So you can substitute all these. So we say that nabla phi at the point 1, 3, minus 2 is going to be equal to, at the point 1, 3, minus 2 to give us, so I'm going to substitute, I'm going to have this to be I into z squared. So our z is minus 2, so this is going to be minus 2 squared minus 4 xy. X is 1, y is 3. So I'll close the bracket. Plus j. Do you understand what I'm doing? Okay, so this is going to be minus 2 into x is 1 all squared plus z, which is minus 2 to our 3. Then plus k into, so I have this to be 2x. That's 2. X is 1, z is minus 2 plus 3, z is minus 2 squared, and y is 3. So I have that.
After text.
You missed this. It's going to give us what? Minus 2 squared, 4. 4 minus 12, right? That's going to be minus 8. Minus 8i. This is minus 2. This is going to be minus 8. Abi? Minus 2 raised to power 3 is going to be minus 8. That's going to be minus 10. And then we're going to have minus 10. and finally
Minus
this
4
is minus 4
minus
so
plus
9 times 4
36.
36 36 minus 4 32 now we plus 32 so we can now find out what the directional derivative is. So this is going to be what? Our derivative is minus 8I minus 10G plus 32 dot. What's this denominator? Square root of what's this? Root 35. So this is going to be multiplied by 1 over root 35. Now I can move out that denominator. Minus I plus 5 minus 3. It's going to give us this multiplied by this. So this is going to be 1 over root 35 into this. That's going to be minus 8 multiplied by minus 1 plus minus 10 multiplied by 5 plus 32 multiplied by minus 2. What will that give us? What do you have in the bracket? What will it give us? In the bracket, what does it give us?
Huh? Now, how did they type now?
Minus 130 over root 35, have you?
New people they try to.
That is that about that.
New people they try to shine this.
This is this and that is that.
Open your phone.
Look at something now. So when will the hello please listen now. When will the directional derivative be maximum? When will you have a maximum directional derivative? Or say along what direction will the directional derivative be maximum? Do you understand what I just said? So think about it. If you want to please pay attention to this, look at how I this up, right? Now look at this. Hello, pay attention to this. If I have now 5, okay, and I am dotting it with a certain unit vector, okay, so that's what directional derivative is going to give us. Okay, if I am doing this, I know normally this should mean modulus of nabla 5 multiplied by modulus of the unit vector multiplied by the cosine of angle between them. Let's see, angle theta between them. Can you remember that? Just product of two vectors. Abi? The magnitude of a unit vector is 1. Abi? So this is basically going to be the same thing as nabla 5 multiplied by modulus of nabla 5 multiplied by the cosine of the angle between them. Abi now? So cosine can carry values from -1 to +1. Abi? Do you understand what I just said now? That means the maximum value that the cosine can be is 1. Is it clear? That means this thing will be maximum when cos theta is 1. Is that very clear?
Yeah.
And when will cos theta be 1? So we say that the directional derivative is maximum when this is 1. When will cos theta be equal to 1? Is maximum when cos theta, that's the cos of angle between it and the particular direction, is 1. Is it very clear now? When cos theta is equal to 1. That's when theta is equal to 0. So theta being equal to 0 degree, that will mean what? When theta is equal to 0, whether degree or radian, that means what? That means the direction is along nabla 5. Is it clear? So that means directional derivative will be maximum along nabla of 5. Is it very clear? So if I want to get the maximum direction of the derivative of a certain function, it will be along the direction of nabla 5. So if I want to get the direction at which its derivative will be maximum, I will just obtain nabla 5 at that particular point. It will give me the direction at which the derivative will be maximum. Is it very clear?
Yeah.
So that's that. Now that. The direction of graph 5 gives the direction in which the maximum rate of change, in which the maximum rate of change of phi occurs. Direction of grad phi gives the direction in which the maximum rate of change of phi occurs. In which the maximum rate of change of phi occurs. Did you get it? So that's the maximum rate of change in phi occurs in the direction of grad phi. So that is how that. Alright, that is the first characteristic or the first behavior of the gradient field. Alright. Another one is that it is normal to potential surface. Write it down. It is normal to potential surface. Yeah, it is normal to potential surface. That means if I define, listen very well, if I define a surface, of course, when you have this in terms of x, y, z, it will generally define a surface in 3 dimensions. So if I define a surface by x, by phi of x, y, z equal to 0. Okay, this is equation of a surface, an arbitrary surface. Please pay attention now. If I define a surface this way, nabla phi is a vector. It's going to give me a vector that is normal to that surface. Is it very clear now? That is, when a surface, for a surface, nabla, phi of x, y, z, nabla phi is a vector normal to this surface. The vector normal. You know what I mean by normal? Perpendicular. Abi? Normal to the surface. Phi of x, y, z equal to 0. Is it clear? So, if I have a surface defined by phi of x, y, z, and I obtain nabla phi, it's going to be a vector normal to that surface as the particular point. You should recall that this was what we used last semester when we talked about equations of tangents and normals. Can you remember that equations of tangent plane and normal line to a surface? Can you remember something like that? Can you remember equations of tangent plane and normal line to a surface? Applications of partial derivatives. What we talked about the fact that the normal vector, the unit normal vector is given by nabla phi divided by modulus of nabla phi. Can you remember something like this? Okay. This was how we defined the unit normal vector last semester. So we are just recognizing what we've done before. Okay, so nabla phi is a vector that is normal to the surface. So if I want to get the unit normal to the surface, I'll divide by the modulus of nabla phi to give me the unit normal to that surface. Does that make sense to you? That's what we mean by unit normal. Alright, so let's move on. And finally, it is.
I'll just leave it in
It is parallel to position vector R. It is parallel to position vector R. Yes, no, yes. It's parallel to position vector R. When two vectors are parallel, what can you say about their cross product and dot product? When two vectors are parallel, what will be their dot product?
It is parallel.
The cross product will be 0.
No, the cross product will be 0.
Cross product will be 0. Dot product is just Alright, so look at this now. So we say it is parallel to position vector R. So you remember that in this class we have established that nabla cross R was equal to 0. Can you remember this? Have we done this together here? Nabla, we saw that nabla cross R was equal to 0. And we have also seen that nabla dot R is equal to 3. Do you understand what I'm saying? Can you remember that? So that confirms what you just said now, that when you have two vectors to be parallel, their cross product will be 0. Is it very clear? So it is parallel to the position vector of R. Is it clear? Did you get this? So we're done with this behavior. So what we want to look at are properties of the gradient, divergence, and curve. Their properties or identity. That is how you can go from one equation to the other. We have done most of them already. Invariably, we have touched almost all of them. So I just want to write them out for you. So you should know all of them by heart. You know all of them by heart. So it means that you should actually play around with them and see how to verify them from the vector algebra relations we have written before, vector differential relations we have written before now. So I'll write them out. So we'll pick them one after the other. To start with, properties of the gradient. The properties of the gradient. Yeah, topic. Properties of gradient and divergence. Properties of gradient and divergence. So I gave you almost all of these as assignments the last time, and we solved them together. We solved some of them together. We said we needed to solve together. So I'm not major work in this section. I'm just trying to pick out things that I think I have not touched. So that's why it's so look at this. Properties of gradient and divergence. Or you can say identities. Gradient and divergence again. So we've written some of them before. So in all of these cases, K, when you see K, after phi and psi are scalar functions. A, B, vector C, K are constant. Together, C and K are some constant. The first relation is lambda of K phi equal to K lambda phi.
From that 3-9 to 4-7.
Don't join them on your thing.
Ana complexe como tá. Foi mais que está ali barulho do tudo, vai a com a machucada, bicho grande né, vai fazer isso.
Try the right now. Try the right now. Why the right now? So now you talk up now. Why? Now okay, you're Scan with your phone. Okay, that's I'll not go back to
Check we go put down for it near.
Now conversion table.
Ball, spin, rotor, they mean the same thing. Ball, spin, rotor mean the same thing.
Me and you forgot the end of that. You said got that like that. VI. Lambda plus lambda.
Pay attention now, pay attention.
No, that's
So I think these ones are, hello, listen now, these ones are quite straightforward to deal with. Listen, all these ones actually follow from your rules of differentiation. Pay attention now, pay attention. All these follow from your rules of differentiation. Imagine that you have ddx outside. Hello, listen please. You can roughly imagine that you have ddx outside here. You want to take the derivative of this function, and this one is a constant. You can move out the constant. So that's exactly what you have here. If you wanted to differentiate a function, also you have this as function and this as function. If you have ddx outside, you can move out the constants and do exactly this. If you want to do the derivative of a product of two functions, you can use product rule. Keep one as constant, differentiate the other plus, keep the other as constant, differentiate the first one. Is that clear? Okay, so it will follow directly. If you want to take the derivative of this also, it's the same way. Abi? If you want to take the derivative of this with respect to x, you just take the derivative of this first with respect to 5. You understand what I'm saying? That will give you n, bring out the power, n 5 is power n minus 1. Then you take the derivative of 5 itself. Yeah. Okay, in this place, Abi? Vector now, vector. Can you see it?
Look at that number 2.
Number?
Number 3 plus constant.
Okay, it's used as a constant.
Wait, is this basket? She makes it, she get hours.
You have one, and this one to be like
Because my dad does my does he have power?
I won't go and
Get something like so.
you get what I'm saying. Please pay attention. The same thing happens. The same thing applies to this. You want to take the derivative using quotient rule. We are going to do bottom the top minus top the bottom. All about bottom square. That's exactly what you have here. Bottom the top minus, that's the bottom, minus top the bottom, all over bottom square. Is it clear? We follow directly that way. So you want to take this is second derivative. So by the time you clear it out, I think we check this together, the other thing, one of the corrections together. You can verify this from that. So this also follows from the same idea. I can move out the constant here. I can move out the constant here. So for this also, I'll follow the same approach, knowing that I'm dealing with a vector. So I must ensure that each portion of my result is a vector. Is it clear? The first one you have nabla 5. So phi nabla, that's the vector. That's the vector A.
It's actually showing
and this one is A dot nabla phi. Nabla phi is also a vector, and that is that.
Is the effect that the person made for this
Second one also follows from the same approach. But the one I want you to take note of, which is very, very, very important, is
how many episodes?
This one in particular, this one here, and this one. Please take note of the difference between these two. Listen very well. You might be tempted to think that because you have nabla A, you have nabla A here, and in this case, you might just think this one will just replace everything you have for nabla. Okay? But that is not so. You will see that when we dealt with divergence, I told you nabla dot A is not the same thing as A dot nabla. You get what I'm saying? Okay, so in this case, what you have here, and then from vector relation that we looked at earlier, we talked about the fact that we have A cross B cross, you can remember this, we said this was equal to A dot C, AB, multiplied by B, minus A dot B, multiplied by C. So, okay, that works fairly well for the first one. Okay, it works fine. You can do exactly that, and you're going to get something like this. But for the second part, look at something this. For the second part, because of this derivative, we're going to do some. We're going to simplify it this way. If you simplify it this way, that will work fine. Just by replacing A, in this case, our A is nabla. When you replace A in that expression, you're going to have this thing to be nabla dot C multiplied by B, abi? You're going to have minus nabla dot B multiplied by C. Okay, so that is what you have here in this case, nabla dot B, nabla dot A. Do you understand what I'm doing?
Yeah.
Do you get what I'm saying? Right. But you won't stop there because this expression, in this case now you have these two of them. Now A dot C is the same as C dot A, but nabla is not such a vector, it's an operator. Nabla dot A is not the same thing as A dot nabla. So you will do the reverse of it also and add that result. So you can see here you have nabla dot B A. Here you have B dot nabla A. Is it very clear? You reverse it, that's the result of it. Okay? So in this second case also, where you have nabla dot A, reverse the expression again. Nabla A dot nabla. Is it making sense to you? Both of them will still carry the minus sign. Please note the difference between this. Okay? Alright, so that is about that. Yeah, so I think you understand this already. I told you yesterday that you can use delta to represent the Laplacian, Nabla square. So anytime you see this delta, it simply means Nabla square. You see the Laplacian operator. Is it very clear? Right, so that is that about that. Okay. So you may be asked to verify any one of them. Okay, I think you can verify them. The default way to verify any one of them. We've talked about this before. For instance, if you want to verify something like this, or you want to prove that this is actually true, you can set a certain vector. You can say let A be equal to A1I plus A2J plus A3K. And you say let B be equal to B1I plus B2J plus B3K. Is that clear? Then you can try out what nabla cross A cross B will and what the other side will give you. You understand what I mean? You get what I just said? So you can do that if you try. It's going to give us nabla cross A cross B. So what is A cross B? You can obtain A cross B. What is it going to give you? A cross B is going to be something like this. I, J, A1, A2, A3, B1, B1, B2, you can complete that. Wait. You know that complete.
We say now. Now.
Yes, I see that. Okay. I into B3 minus into A3. You have let's do plus J. So that's going to be minus plus K.
Yes, side.
I've changed it now. I've changed doesn't matter. Alright, so what else? Under cross A cross B. That will be equal to what? So let's write out A cross B. So that's going to be somehow long. So we can have this to be A2B3 minus and the next one, A3 minus A1 B3. And last one, A1 B2 minus A2 B1. We have this I del LX, del Y, del so the I components is going to be what would this give me? It's going to be del LX, del Y of A1. Let's pick them component by component. I know the X component is going to be del Y of A1 B2 minus A2 B1. You get that? Minus del C of A3 B1 minus A1 B2. If I simplify this one, that is going to be if I want to differentiate this, I have to use the product. It's a product of two compounds. So I'm going to have this to be A1 del B2 del Y plus B2 del A1 del Y. Then I'm going to pick the next one, minus of this. This is going to be A2 del B1 del Y minus B1 del A2 del Y. Doesn't make sense? No. You get that? This is going to give us the next one. Minus, it's going to give us A3 del B1 del C minus B1 del A3 del C. It's going to give us minus so we have done the first one. Minus here we have set that now become plus del A1 del B3 and that is that. So you can see the ones carrying A1 and the ones carrying A2. So for those carrying A1, if you put them together, you're going to have this to be A1 and A2 is going to be del B2 del Y minus del B3 del C. What else? The one carrying A1
So that is minus.
Which one is plus?
Didn't follow, huh?
Which other ones are common? B1 and B. We have B1 to be common. It's going to be minus B1. Then A2 then Y minus plus then A3. What else? We have just one, Abby.
But wait, see people they collect this video. Anybody don't come to say they want this video. Okay,
There's no other one I don't again.
okay.
Alright.
Usually
We have
give the video for like.
let's
Only
mark
give
the
him the
ones we
video
have.
for limit.
A1 and A1. We have
Show
B1
men.
and
Finish and you.
C1. These are the ones we have left. You can see we have this to be del A1, del Y, and this one is del A1, del C. So
What did that grant do?
all of them is going to be equal to
That's right, that's right.
plus B2, then A1, del Y, and next one. That's for the X components. We do also the Y components and the Z components. Then put all of them together. This is going to give you what? But you can do that, that's fine if you want to do it. But the point is that you're going to get the vector. So if you have one component of the vector, you should be able to tell if the two of them will be the same. If I have the X component of this one, and I have the X component of what I have on the other side, I can tell if they are the same. Do you understand what I'm saying? You get what I just said? If two vectors are equal, their respective components will be equal. Abi? So what I have here, if it is equal to, what I have here, if it's going to be equal to this, then their X components have to be the same. Does that make sense to you? Did you get what I just said? Aha. So I actually don't need to expand for the others. Basically, I've expanded for the X component. I can now come to the other side and expand for the X component and see if it's going to be the same thing as this result. You understand that? You can expand now. You have already written the representation for A and B, Abi. So you can get for each one of them. Do you understand what I'm saying?
Yeah, you should.
You get that? You get that?
I don't get it.
That's not good.
So look at it. What is this one going to give you? Lambda dot B. Lambda dot B is going to give you a scalar, Abi. That is going to be del B1 del X plus del B2 del Y plus del B3 del C, Abi. Then you want to multiply it by A. Is it making sense to you? So multiply by A1. Yeah, you're going to multiply by A1. Since you want the X component, is it very clear? So if you are dealing with the other side, for instance, the X component from the other side, that is going to be multiplied by A1, Abi. So that is going to be A1 multiplied by del B1 del X plus del B2 del Y plus del B3. You understand that? Okay. Then you pick the next one, minus B. So lambda dot A is going to be what? That will be del A1 del X. So this is going to be minus B1 into del A1 X plus del A2 del Y plus del A3 del C. You understand that? Then you pick the next one again. B dot nabla. That's going to give you what? So that's going to give you. So you have here. This is going to give you. In this case, B1 del X. Do you get that? And then this one is going to be a vector. So we are going to have B1 del X of A1 together. So that's going to give you this to be plus B1 del x of A1 Abi plus, you know, this one is a scalar itself. You carry all of them. So that would be plus B2 del y of A2 plus B3 del LC of A3. Does that make sense?
No, I thought the A was A1.
Oh, sorry. Which one? So the last one. A dot this. That will now be minus A1 del x of B1 minus, minus if I affect all of them, minus A2 del y of B1 and minus A3 del z of B1. Does it make sense? That's all. So we can see if we can cancel out some of them. Is it making sense? Alright, so you have this to be A1 del B1 del x, Abi. So it can only cancel this one, Abi. So what else? You have this to be B1 del A1 del x. This one can cancel this. Does it make sense? Alright, so that's all, Abi. So we are going to have this, and this. They are all different now. There's no other one that is right. So you can see if they are going to be the same, if they are the same thing as what you have on the other side.
You don't analyze them to
Are they the same?
Yes.
Okay.
I love that.
So those ones carrying A1, Abi. That's it. This one and this one.
Don't worry, tomorrow I will beat your record.
Can you see that? Those carrying B1. These
I
are
will beat and so
these
say
are
you send
and then the ones you have left. These are main and this. Does it make sense to you? So that shows that. So that's the way you can confirm it. Is it clear? Okay, so thank you. So that kind of thank you. Alright, thank you for coming. So we have a test on Thursday. Thank you.